Welcome to video 3.3 in our first Principles of Astrophotography series. In this video, we show how the declination of a celestial object can be used to determine whether this object can be seen from your latitude. That is, whether it is ever above your horizon.
Does that mean that there are objects in the sky that I can never see from my latitude, no matter the time of day or season of year?
Yes. The only exception is if you live at the equator, where you can see everything in the sky.
Well, I guess I'll have to brush up on my Espanol and move to Ecuador.
Good idea. Send me your pictures. We show that celestial objects come in three visibility classes that depend on your latitude. Circumpolar objects that are always above your horizon, seasonal objects that rise and set each day, and antipolar objects that are always below your horizon.
And we show how to determine which celestial objects are in each of these three classes based on your latitude.
This video is based on section 3.3 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. All right, Principle 19, local directions. Your horizon is the plane that is tangent to Earth's surface at your location. Your zenith is the point directly overhead, and your nadir is the point directly underfoot.
Reminds me of mater in cars.
Like ta mater, but without
Like
the ta.
ta mater, yeah. Okay, so here's a man on a cruise ship in the Atlantic Ocean in the northern hemisphere.
And he remembers to look up.
And he's remembering to look up. And when he looks up, straight overhead is his zenith. Directly underfoot is his nadir. And then his horizon is the plane that is tangent to the Earth where he is standing. So my horizon is different from the horizon of somebody up in the North Pole or wherever. Your horizon depends on where you're standing.
20. Visibility classes. Stars and deep sky objects come in three visibility classes that depend on the observer's latitude. Circumpolar objects are always above the horizon. Seasonal objects spend time both above and below the horizon each day. And antipolar objects are always below the horizon.
Let's talk about visibility classes at poles.
21. For observers at the North and South Poles, half of the celestial objects are circumpolar, and the other half are antipolar.
Now, we poked around to try and find a word that describes, I've taught astronomy before, and a lot of times we'll say that stars come in two classes, circumpolar and non-circumpolar. But that doesn't distinguish between the non-circumpolar objects that you can actually see, which we call seasonal objects, and the ones that you can never see, which we call antipolar. They're in the direction of the opposite pole. So for this observer at the North Pole, his horizon is now tangent to the surface as always. This is his point straight overhead, and his zenith is pointing toward the North Star, right? And his nadir, as always, passes straight through the middle of the Earth. So what can he see? At this point, this is a diagram of where things sit with us seeing North and South America and seeing that observer standing at the North Pole. 12 hours later, the Earth would have rotated on its axis, and we sitting out here in space can see that both the Earth and that observer have rotated, and we're now looking at Africa and Asia. But what has happened with the stars? The stars that he can see are exactly the same stars. The North Star is still up here at his zenith, and whatever he saw over here got rotated over to here. So stars are going around in circles, circling around the North Pole, and so as the Earth turns on its axis, he can see the stars turning in circles around the North Pole. This is pretty cool.
Make for a cool picture.
Yeah. Yeah, that really would. Now, on the other hand, all these stars below his feet, he never gets to see. They're all antipolar. They're always hidden by the Earth. Now, he sees half of the stars on the celestial sphere, and I might ask Ren how the celestial equator. So the celestial equator divides the celestial sphere into two halves, the northern celestial sphere and the southern celestial sphere. And how is that celestial equator defined?
Well, it is his horizon.
It is his horizon, and you're claiming that this is the celestial equator right here, but I thought the celestial equator was straight above the
But
equator.
you forget. Things are so far away that it makes no difference to him.
That's exactly right, Ren. Well done. So, remember in a previous video we talked about the fact that even the nearest extrasolar star, called Proxima Centauri, is so far away that it would take 9 billion Earth diameters stacked on end to get there. And so if you want to put the celestial sphere where Proxima Centauri is, pretend all the stars are pasted against that sphere, then this distance between the Earth and Proxima Centauri is 9 billion Earth diameters. So if you want to get to scale diagram of it, you're going to have to shrink this Earth down to even smaller than what I've shown it here. It's just a tiny little period here. So the bottom line is that Ren is exactly right, that once you shrink that Earth down to its proper size on the cosmic scale, you could care less about whether you're talking about the horizon of the observer that's at the North Pole or the celestial equator, because they're both going to coincide with each other.
Right.
Exactly. Well done. All right. So let's put him on the South Pole and see what he can see. He's pulled toward the center of the Earth by gravity, like we all are, and his overhead direction is straight toward the South Pole, South Celestial Pole, down where the Southern Cross is, and his nadir is again through the Earth, and his horizon is like that. So his horizon also is effectively the same as the celestial equator. So down here, this observer at the South Pole can see all the stars in the southern celestial hemisphere, whereas the observer at the North Pole can see all the stars in the northern celestial hemisphere. See, each of them can see only half the stars. And again, these antipolar stars, the northern stars, for this southern observer, are always going to be hidden by the Earth. Okay, here he is after the Earth is rotated, but I think you have the idea there.
22. Visibility class at equator. For observers at the equator, all celestial objects are seasonal.
So there's only one class at the equator, one visibility class, and everything is seasonal. What do we mean? If the observer is right here, so we're out in space, looking down at the Earth, looking down at that observer that's standing in looks like the Atlantic Ocean. And then we watch to see what happens after the Earth has rotated 12 hours. So 12 hours later, we're still in the same place in space. 12 hours later, now we can see the Africa and we can see Asia, etc. And the observer has rotated over to the left side of the Earth instead of the right side. So now this observer can see the stars that were on the other side, on the left side of the Earth, whereas here before he could see the stars on the right side of the Earth. So this guy is going to be able to see all the stars in the sky. And except that Ren pointed out that it's going to split the North Star. He's only going to be able to see half of the North Star at any given time. But over time, right, you'll be able to see the whole thing over time.
Yeah.
Now, the reason that we call these stars seasonal is that if there's an object that you're interested in and it's out here in the sky, and the sun also happens to be in the sky at that same time, you're not going to be able to see that object because it's going to be up in the daytime. So he would have to wait until the Earth has moved in its orbit 6 months to the other side so that he could then see this object at night. So during the daytime, this guy can't really see the stars because the sun is obscuring them all and blotting them out. At the nighttime, when he's over, if the sun is right here, at nighttime he'll be able to see the stars over on this side. Then 6 months later, he can see the stars on the other side. I don't know if I explained that very well.
No, I think the sun is the
sun is the killer there.
That's the killer. Yeah, it's the worst light pollution ever.
Yeah. So they're seasonal objects because you can only see them at certain seasons of the year when the Earth and the sun are placed in the right spots. All right.
23. Visibility classes at mid-latitudes as an observer moves from the equator to the north or south pole. Seasonal celestial objects gradually convert into circumpolar objects and antipolar objects.
Yes. So remember, at the equator, there was only one class. It was seasonal. And as you move, in this case, north, then some of these seasonal objects get converted into circumpolar objects, and others of them get converted into antipolar objects. So the antipolar are easy because there's no way, no matter what time of day or time of year, he's never going to be able to see these antipolar objects because they're always going to be hidden by the Earth. So when he's rotated to the other side of the Earth, 12 hours later, he still can't see those stars that are hidden by the Earth. These seasonal ones and then circumpolar are the ones that he's going to be able to see all day and all night. All day, if the sun weren't there, he could see them, and but they just circle around the poles for him.
This is why the Southern Cross was always antipolar for me, except for when I was in Australia.
Mm-hmm. Yeah. All right, the same kind of thing happens here in the southern hemisphere, but now the roles are reversed. The circumpolar objects for this fellow at mid-latitudes, and by mid-latitudes I just mean not at the equator and not one of the poles, that this guy, the circumpolar objects are going to be circling around the south celestial pole like you saw in Australia. And then the antipolar objects are going to be the ones that are up in the north. And here it is rotated. All right, so this is a beautiful photograph of circumpolar objects. And I think it was taken in the northern hemisphere.
They got some really bad star trails on that.
They did. Yeah, so star trails are something we try and avoid generally in astrophotography, but in this particular case, they're what we're looking for. Yeah, they're really pretty. I think this is the actual North Star. As I remember, this was taken. I got it off of Wikimedia.
Oh, so the North Star wouldn't actually be cut. It would wobble in and out.
Yeah, it would wobble in and out of the field of view because the North Celestial Pole is right here, and the North Star isn't exactly on the North Celestial Pole.
I like it better when it's exact.
I'm so sorry.
Yeah.
So yeah, that's what circumpolar stars do. During the course of a day, they'll circle around. They're always above the horizon, not necessarily always visible because of the sun. This is a long exposure photograph of the northern sky taken of the Kitt Peak Astronomical Observatory in Arizona in the United States. Arizona is in the northern hemisphere. And so what you're seeing is the northern horizon here, the North Pole, and this is taken at night so you can see the stars. You can see that the stars are circling around the North Pole, North Celestial Pole. Some of those stars complete the entire circuit. So this star, etc., right here, rotates counterclockwise, makes the entire circuit, although half that circuit takes a whole day to go around. So you don't see any circles that are completed. You just see segments of circuit of the circles of these stars. The reason is you can't, if you took it for 24 hours, then roughly half of that time would be during the daytime and you couldn't see the stars. So, but if you could see the stars both day and night, you could follow a star around this circuit that I just showed. The stars that follow this yellow path also circle counterclockwise, but they're the ones that just skim the horizon. Anything inside of this circle is a circumpolar star because it's above the horizon all day, 24 hours a day. The stars that are outside of this yellow circle rise in the east. So if this is north, then over here in this direction would be toward the east. They rise in the east, they reach their peak, they come down, and they set in the west. Those are called seasonal stars. This is also the view that observers in the southern hemisphere have of the southern celestial pole. So now these observers as we talked about before, these observers are looking south. So instead of north, we're going to be looking south. Instead of the North Pole, we're going to be looking at the south celestial pole. And now if we're looking south, then this direction must be west, and this direction must be east. So what happens then? These stars that circulate around the southern celestial pole circulate clockwise. So now these guys are going around in this direction, in a clockwise direction. Instead of this, we have them rising. Again, they're still rising in the east. They always rise in the east. They get to the highest point and they come down, and now they set in the west. But the important thing is that in the southern celestial hemisphere, you can see the southern celestial pole, and you can see circumpolar stars circulating around that southern celestial pole in a clockwise fashion. And again, just like in the northern hemisphere, stars are going to rise in the east and set in the west. That's that's the result of the Earth's rotation. So what happens when you're in the northern hemisphere and you're looking south? So now we're in the northern hemisphere. This is a photograph taken in Iran. And this is the southern horizon from a location in the northern hemisphere. Well, the southern celestial pole is blocked by the Earth. It's below the Earth. And the stars that are near that southern celestial pole are antipolar. Like we discussed before, you can't see them. You never see them. So the southern celestial pole is going to be somewhere here down below the horizon, and you can see the circles of stars that are going to, see, this is south, and so this would be west on this side and east on this side. They're going to rise in the east and set in the west. None of these stars are circumpolar because all the circumpolar stars are hidden. There aren't any circumpolar stars because you're in the northern hemisphere looking south. They do rise in the east and set in the west. So they travel from left to right as they travel across the sky. So that's the view of the southern horizon from the northern hemisphere. What about somebody who's living in the southern hemisphere, down in Australia or wherever, and they want to look north? Well, what they see is now, if they're looking north, and this has to be east, because if you look north, then your right hand points east, your left hand points west, and stars are going to rise in the east and set in the west. So those stars, as seen by a southern observer looking north, travel from right to left across the screen, and you only see seasonal stars when you're looking toward the opposite pole. The important thing is that this is what these two figures are what you can see when you look north or south from either hemisphere. You don't ever see the antipolar stars because why? Well, they never rise above the horizon. All right, let's do a little exercise to see if we understand this. And we, in our book, we go into a little bit more detail on the mathematics, but this example is really, I think, instructive. So Ren and I live here in Logan, Utah, in the United States at a latitude. So lambda stands for latitude, as we talked about in a previous video, of 42 degrees. So this is roughly 42 degrees. The exercise now is to ask the question about Bode's Galaxy, the Ring Nebula, and the Tarantula Nebula. Are they circumpolar at our latitude? Are they antipolar? Or are they seasonal? That's what we're going to do. So let's first look at Bode's Galaxy. What would your guess be for Bode's Galaxy?
Well, since it's above our latitude, it's going to be circumpolar.
Your guess is a circumpolar, and I think you're right. Let's check back. So Bode's Galaxy is a latitude of 69 degrees. So these dividing lines between seasonal, antipolar, and circumpolar are given by these equations. So that's this delta is 90 minus lambda is the dividing line between circumpolar and seasonal. Well, let's substitute our latitude, 42 degrees, and 90 minus 42, it better be 48. 48 degrees. And so an object that's between a 48 degree, and this is the declination, as we talked about in a previous video, the Greek letter delta. Circumpolar objects are going to be between a declination of 48 degrees and 90 degrees. 90 degrees is as far as you can get with a declination.
Right.
Okay? And is Bode's Galaxy, is the declination of Bode's Galaxy between 48 and 90?
Absolutely.
So Bode's Galaxy is circumpolar. All right, what's the dividing line between seasonal and antipolar? That's this guy right here. So in this case, I want this angle, the latitude 42 degrees minus 90 degrees. So 90 is bigger than 42, so we're going to get a negative number, and that's really super embarrassing, right?
Yeah.
But then we realize, no, that's not embarrassing. We know how to deal with negative numbers. If the number is negative, we know it's in the southern celestial hemisphere. It's not embarrassing at all.
Mm-hmm.
What are you talking about? So this is going to be a negative 48 degrees. And that's the dividing line between seasonal and antipolar. So let's look at the ring nebula now. So this dividing line here is at 48 degrees. This dividing line here is at negative 48 degrees. So where does the ring nebula fit?
33 is this, between those two.
Between those two.
Yeah.
So the ring nebula will be
Seasonal.
Tarantula Nebula,
Oh.
negative 69.
We're going to have to make friends in Australia.
We're going to have to make friends in Australia because antipolar objects are between negative 90 and negative 48. And Tarantula is negative 69.
Yes.
Luckily, we do have a collaborator in Australia who shot that for us when we were back in our Sea Star days. So this is antipolar. So we've got one example of each of the three classes of objects. Do one more example, is that all right?
Oh, great.
Let's put the observer in Santiago, Chile, at a latitude of negative 33, and that negative sign means what, Rand?
They're below the equator.
Below the equator, it's in the south. And so now we're going to put this value in here. So let's find out what this one is.
I'm betting 57.
Sorry? 57, that's right. Negative 33 degrees plus 90 degrees. It's going to be 57 degrees for this dividing line between antipolar and seasonal.
Right?
Let's do this dividing line between seasonal and circumpolar.
This feels repetitive.
Yes, it does. So
Couldn't we just put a negative in front of our 57?
we can.
Okay,
We
great.
can. It's going to be negative 57. And the other way you can do it is just to say lambda itself is negative 33, and the negative of a negative is a positive.
Right.
So that gives us 33 minus 90, which is 57 degrees. Negative 57, and then 90. All right, so here's our three dividing lines. Well, delta is 90, declination 90, declination of 57, declination minus 57, declination of minus 90. So antipolar. So talk about Bode's galaxy.
And Bode's is at 69. Oh, 69 is greater than 57.
So
So it would be-
69 is up here
It
somewhere.
would be antipolar.
It's antipolar. Ring nebula.
33. You know, Ring Nebula is great. A lot of people could see it a lot of the time.
A lot of people can. So it's between negative 57 and 57. So we're
You
good
bet
to go
it
as
is,
being
yeah.
seasonal. And then Tarantula Nebula, which was antipolar before.
Yeah, it's polar. It's circumpolar. Yeah.
So probably for Caroline down in Australia, it's Tarantula Nebula circumpolar.
Yeah. It's easy pickings year round.
Thanks so much for watching.
And we'll see you next time.